Hello everyone. Welcome to the live section of this course, which is Quantum Transport. So I'm Gitanjali. I'm a PhD scholar from IIT Delhi, and I'm the TA for this course. So, and during the last section, we have gone through the contents and we have solved few problems related to the concept of week 10. So in this live session, we'll go through what are the concept that has been covered in this week. Also, we'll try to solve the problems related to the concept of this week, and also I will try to solve few problems from week 10 that I haven't solved in the last week. So, so if you recall, in this week, we basically see what are the different types of measurement standard for measuring the resistance or measuring the voltage or current for a quantum electronic devices. So just like if you want to measure anything, you need a reference, right? So if you want to measure the length, you need a scale for that. And the unit for the smallest unit is the SI unit is in the unit of meter. So similar to that in quantum devices, we need some standard so that we can measure the resistance or voltage or any electrical properties of that device using a known measurement standard. So we have seen three types of measurement standard in this week. So we have gone through first, we have seen the resistance standard, then the voltage standard, then we have seen the current standard. So, in the first part of this live session, I will try to cover in brief what are the different type of how this measurement standard uh, has been discussed and what are the different concept related to that. Then we'll try to solve the problems related to the concept of week 10 as well as week 11. So if you recall, there are seven base units that has been discussed so far to measure the different parameters of a system. So these are the seven measurement units that has been well defined using different SI units. So you can go through all of this. I'm not going into the detail. So the definition, these are already well mentioned in the table. So if we look at first we look at what are the resistance standard and how we can measure the resistance of different devices using the quantum Hall effect. So as shown in this picture, resistance of a nano electronic devices, you can standardize the resistance using the quantum Hall effect. So this we have seen in details in one of our live session. So this is the you can see these are the voltage and okay, there is a doubt. Week 11 assignment also are from week 11 or week 10. Uh, I think the first part of the assignment are from week 10 and the next is from week 11. Some of the questions, I think most of the questions are from radio frequency ACT. So I will try to cover few problems related to that concept so that it will be helpful to you to solve the assignment. Okay. Okay. So for resistance standard, we use the quantum Hall effect. Let us see why we are using it. So this plot. I think this is already familiar to you. But this is the voltage, the longitudinal voltage versus the magnetic field, or the transverse, or we call the Hall resistance versus the magnetic field. So for the longitudinal voltage, we see, if you recall, we see oscillations in this voltage. These are called Subnikov-Diaz oscillation. And we have gone through in detail why we are getting these oscillations. So in contrast to this Subnikov-Diaz oscillation, for the Hall resistivity, we have seen as we increase the magnetic field, we see step-like manner, step-like increment in the Hall resistivity. So, and these levels, they have different filling factor. So this filling factor, it is related to the Landau level. How many Landau levels are occupied for a given magnetic field? And as we increase the magnetic field, the Landau levels, the value of Landau level decreases. So these are just to recall you what are the concept that we have covered in our previous lab session. So so the main point that we are interested is the Hall resistivity, and we are from the graph we can see that these are constant for a given set of magnetic field. So this constant value we have expressed this in terms of h by a square 1 by n. So n here it is nothing but this is the filling factor that we have seen before. Okay, and h by e square it has a value of 25.813 kilo ohm. So from the definition, we can see that the Hall resistivity it is expressed in terms of fundamental constant, which is h by e square. So it doesn't depend on any material parameter like whether we are measuring some different material or the dimension is different. So it doesn't depend on any of it. So that means it will remain constant even if we vary this external parameter. So this is what has been detailed in these three plots. Okay. So if we look at the first two plots, so this is these two graphs. It shows what is the error that we will get when we vary the device width. And we have in the measurement they have considered only two plateaus like plateau 2 and plateau 4. Okay, so if you recall, if you see this from the first plot, if you see this delta R by R, it is in the order of nano ohm per ohm. So that means the errors are in the order of nano ohm per ohm. So if you have a value of, let's say you have a value of resistance, the error will be occur at the ninth place of ninth place after the decimal. So that means the error is quite, we can neglect this kind of error. The error is quite minimal. So, and for I4 also, this same observation, we can see that this is in the order of, let's say this error bar, I think the color is not visible. This error bar, we can see that this is in the order of, let's say around 4 nano ohm per ohm. So it's still in the order of nano ohm per. So that means even if we increase the device width, then it's still possible to get the constant value of Hall resistance. And in the second plot, one of the temperature, we vary the temperature for a MOSFET based devices. And from this plot also, we can see the same observation, like the error bars or the errors, they are in the order of nano ohm per ohm. And we can see the same from when we vary the carrier concentration by varying the gate voltage. So that means from all these experiment, from all the observation, you can say that the Hall resistivity, it's kind of a universal constant, and it doesn't depend on any device width or temperature, or it doesn't depend on the carrier concentration. So that means we can use it to measure the resistance of some unknown device that we don't know the resistance. Okay. In the second part, we have seen why we nowadays why we use the graphene based resistance standard. So all these experiment these experiment, they are for bulk two-dimensional electron gas like gallium arsenide or aluminum gallium arsenide. But if you look at the graphene-based resistance standard, so if you look at the first plot, so from the red, let me take color. From this red and from this blue plot, the blue one is for gallium arsenide and the red one is for graphene. So if you compare this, you can see that as compared to the gallium arsenide, the red one it's showing wider plateau. That means for a wider value of magnetic field, it can still show a constant value of the Hall resistivity. So that means this graphene standard, they are more robust than the gallium arsenide that the scientists have used before. And also other observation is that you can see that the red curve is these are measured around frequency around temperature 100 Kelvin. But for gallium arsenide, it is in the order of some uh, Kelvin and or some sub Kelvin. So that means gallium arsenide, they require low temperature treatment to show this precise Hall plateaus. But if you consider the graphene, even if temperature is high, you can still see this wider and constant plateau for a graphene based as graphene based resistance standard. So these wider plateaus, it's all because of if you look at the graphene, the Landau labels, they are widely separated. So that means even if we increase the temperature, there won't be any much thermal broadening. So that means these effects are not quite affected even if we increase the temperature. So this is why we use the graphene as a standard, because it can show the behavior even at high temperature, and also we can still see the same accuracy. So you can see the accuracy will be in the order of nano. Okay, so this in the second from this plot, so this is for this plot they have compared what is the resistance that has been measured using the graphene as a standard, or what is the value of resistance that has been measured using gallium arsenide as a standard that they have used before. And the plot, it's showing what is the error between these two measurements. So if you use graphene and if you use gallium arsenide, then what will be error? Because now we are using graphene, so that means the error should be less. The error should be in the order of nanohm or lower than that. Otherwise, we can't use it as a standard. Okay. So if you look at the graph, the plots, you can see that the error bar, they are in the order of, let's say, 1 nanohm. Here it is in the order of 3 nanohm. So this is in the same accuracy that we have seen for the gallium arsenide. So that means the accuracy is not affected if you use the graphene as a standard, but if you use the graphene, it's still possible to see the robust or plateaus even if you increase the temperature. So this is what is the main point that you should look for when you using the graphene as a resistant standard. Okay. So in the next case, we the earlier one is for using uh, resistance standard measurement. Next, let us see what are the what are the measurement standard for the voltage. So if you recall, we use quantum Hall effect to use resistance measurement standard, but for the voltage standard, we use the inverse AC Josephson effect. So let us quickly go through what was the inverse AC Josephson effect that we have seen earlier. So it's like if you apply a voltage Give me a minute. So for this one, we have, let's say we Josephson junction means we have two semiconductor, two superconductor that are they are coupled through one tunnel junction. Okay, so there is a tunnel junction here. So this is what we mean by the Josephson junction. So for this Josephson junction, if we apply a DC voltage as well as a AC voltage cos omega t. So this is the DC part, DC voltage, and this is the AC voltage. And we have a condition that V0 it is much greater than nu. So whenever we apply this kind of voltage, both AC as well as DC, so if you recall, we have seen that the current through this Josephson junction, it is non-zero. It won't be zero when we have a angular frequency omega is n q vn by h cut. So if we rearrange it, vn would be n h cut by q f or n h by 2e f, or we can say nf by kf. Kf is h by 2e. So that means the current through this junction would be non-zero whenever uh, the frequency of the AC source that we are using, it matches with this DC voltage. So that means there will be a phase locking between the frequency of the AC voltage and the phase of this Josephson junction. So because of this phase locking, so that means what does this mean? So we have a voltage V0 plus nu cos omega t. So omega can be anything, but we have seen that if omega is n q vn by h cut, then it's possible to see current, non-zero current across the junction. So that means if we sweep, okay, so let us see the plots first. If you recall, whenever there is there is only AC voltage, you have seen a graph like this, right? IV characteristics shows the graph like this, somewhat like this. I think it's already mentioned also. Yeah, this is the plot for when the frequency is zero. So we are just applying the DC voltage. But the moment we turn on the AC voltage, that is frequency is not zero and the frequency matches with this condition. So we will see steps in the voltage. So we'll see constant voltage across this when we vary the current. So when we increase the current, so whenever the current is increasing across the junction, we see a constant voltage uh, whenever the condition Vn is Nf by Kf is satisfied. And these are called Shapiro steps. Okay. So this is what we mean by that voltage standard. It's based on the Josephson effect or AC Josephson effect. And just remember the value of Kf is 483.6 megahertz per microvolt. Okay, this will be helpful to solve the problem. Next, what we have seen is these are some of the plots of, I think, some of the semiconductor junction that has been studied to see the Josephson effect or the constant voltage curve. So if you look at the first plot. So in the first plot, they varied the frequency. From this, you can see that when we vary the frequency from 9.3 to 24.85, we can see the voltage steps, the Shapiro steps, as well as we see that as we increase the voltage, the plots are getting somewhat wider. Okay, this is one of the observation that we see in the first plot, and in the next plot, which is based on NB-based Josephson junction, you can see that from this plot, when there is this plot, this when there is no RF frequency, it is matching uh, what is the IV characteristics earlier. But the moment we turn on the voltage, then we'll see the Shapiro steps. Okay, and for to get this, we need Vn is NF by K. K value directly. Okay, one thing you can do is, so there is no point of remembering K. If you don't want to remember, it's fine. But remember what is the expression for KF. KF is H by 2E. So that means these are fundamental constants. So you know the value of H. It is around 6.63 into 10 to the minus 34 and is 1.6 into 10 to the minus 19. So from this you can calculate the same value that is 483.6 megahertz per micro. So no need to remember, you can just remember the expression. The expression is fine. Okay. So in the next part, what we've seen is if you see these, I think, okay, yes. So if you see the voltage value, that is Vn is Nf by K, and Kf is 483.6 megahertz per microvolt. So that means if you look at this value, the Vn would be, it would be 1 microvolt. So when you apply a frequency of around 500 megahertz, let's say, so this will be order of 1 microvolt. But even from the values, you can see that even if we apply higher frequency, the voltage value we are getting is much, much less. So 1 microvolt, it's not practical, it's not a quite practical value to measure using the measurement standard. But and so to increase the voltage, so to increase the Vn, that means we need to increase the frequency, right? Vn is directly proportional to frequency. Others values are constant. So uh, one way to measure to increase the voltage is to increase the frequency, but it's not quite practical to increase the frequency across one Josephson junction. So there are technical difficulties for that. So that is why to get higher voltage, one thing you can do is to increase this Josephson junction. So to align this junction, many junction in series, so that the total voltage would be the summation of the voltage of each junction. So in this way, you can increase the voltage of a voltage standard. Okay, I think this is what has been covered in this slide. So if you consider 20,000, around 20,000 junction, then you will get a voltage of 10 volt, or if you take this amount of junction, you will get a value of Josephson standard is 20 volt. Okay, so in this way, so that is why we make a array of Josephson junctions just to make a just to get a practical value of voltage so that we can measure it whenever you are using this as a standard for voltage. Okay. In the last part, this they have shown the what is the accuracy of this Josephson standard. So if you recall, for resistance standard, the errors they are in the order of nano. So error is quite less. So let us see what is the errors in calculating the Josephson standard. So to calculate the error, what the experiment has been done is that, so they have taken two Josephson junction. One is here, so one is here, and they have applied the same AC frequency across these two Josephson junction. So that means the phase locking or the Shapiro steps for these two individual Josephson junction would be same. So that means you can say it can the first Josephson junction can record a voltage of, let's say, V1, or it can record a voltage of V2. But practically the V1 is equal to V2 because the frequency is same and they are similar Josephson junction. Uh, okay, sorry, they are different, but they have applied the same frequency. So that means if there is an error in this while measuring the voltage standard, if there is error means the V1 is not equal to V2. So there will be a voltage difference that will be created across the circuit. And because there is a closed loop, there will be a current that will flow across the circuit, and this current will pick up by this RF squared. So in this way, they have measured whether there is an error in measurement of using Josephson junction as a voltage standard. And what they have found that the average voltage difference, that is V1, the delta V, which is V1 minus V2, it is less than in the order of 10 to the minus 21. So that means they are quite accurate for our experimental measurement. So we can use the Josephson junction to use it as a voltage standard. But remember that we need a area of junction to get a practical value of the voltage. Okay, so this is all about the resistance standard as well as the voltage standard. Now let us quickly see what is the current standard. Okay, so for resistance standard, we use quantum Hall effect. For voltage standard, we use Josephson effect, or to be accurate, we use inverse AC Josephson effect. For current standard, we will use the Coulomb blockade oscillation of the single electron transistor, so that we can measure the current by tracing whether we are able to see the charging and discharging event of single electron transistor. Okay, so before 2019, what is the current standard for this measuring the current? It is so these are typically defined that so the unit for current, it is 1 ampere, and this 1 ampere, it is defined as a current that will flow through this two straight wire, whenever there is a distance of 1 meter between them, and they experience a force of 2 into 10 to the minus 7. Okay. But if you look at this definition of ampere, they use meter, also they use volts. So, and if you compare it to the resistance and the voltage standard, so this voltage and resistance standard, they use only fundamental constant, only H and E. But here in the current standard, there is a unit of force as well as unit of length. So that means these definition of current, it is not well defined, so we need more accurate definition to define 1 ampere. So for that, what has been done is that after 2019, the ampere it is defined as a ratio of charge per unit time. So how many charges are flowing across a junction for a given time or for a given frequency. Okay, so these are the charge definition. I'm not going into the details, and this is the Coulomb definition. And if you take the ratio of it, you will get that 1 ampere. It is nothing but the time that is required to flow this amount of electron across a junction, which is 6.24 into 10 to power 8. Okay. And if you look at this doesn't involve any, this only involves time as well as the number of electrons. So that means it is universal. So the straightforward way to define the current for the measurement standard is to express in terms of charge per unit. Okay. And this is one of the expression that you should remember. So you can express the current as E times F. F is the frequency of the flow of electron. Okay. So in the next part, so to measure the currents and to transfer the current so that you can count the currents. So one of the best technique that you can use is the single electron tunneling in single electron transistor. So if you recall in single electron transistor or single electron island, the tunneling happen one by one. So there is no uh, continuous flow of electrons. So that means if you use that, you can count individual electron and you can measure the current through the device. Okay. So this is what we have discussed before also. So single electron transistor, it is nothing but a quantum dot which is capacitively coupled to a gate voltage. Also this quantum dot, it is tunnel coupled to the source as well as the drain side. And if we are in the low bias regime, then uh, there won't be any current and there won't be any tunneling. But if you increase this gate voltage, that means you are changing the Fermi level of this quantum dot, then it's possible to tunnel the electron from source side to the drain, to the quantum dot, and from the quantum dot to the drain side. In this way, we can change the electronic state of this quantum dot from n to n plus 1. When we fill the electron from the source side, then back to n when this electron tunnel back to the drain side. So, but one of the main issue with this single electron junction is that you can these are quite random, so you can't control in a better manner for this single electron junction. So there will be co-tunneling where the same charge they can occupy the different position. So to get a more accurate tunneling, what you can do is that you can increase this single electron transistor. So instead of one, you can use two. And if you recall, for this double quantum dot, you can uh, control the what is the Fermi level of this second quantum dot as well as the first quantum dot by using this gate voltage, and you can lock the electron here by increasing either this by changing this voltage so that it can lock here, or you can make the gate voltage of this such that it can tunnel to this side. So in this way you can tunnel this electron in a step like manner. Okay. And for this double quantum dot, you can, if you recall, we have get a hexagonal pattern of this charge stability diagram. So, which is, I think, so let us discuss the metallic single electron pump, which is based on the double quantum. Okay, so there are two types of pump that has been that you can use for the current standard. One is metallic single electron pump, or another one is based on the semiconductor electron pump. But the better one is semiconductor one. Okay, so let us see the metallic. Then let us discuss some of the issue with this metallic single electron pump. For metallic single electron pump. What do we mean by metallic single electron pump? So this means this tunnel junction, they are made up of metals. Instead of a semiconducting tunnel junction, we have a metallic tunnel junction. So we have double quantum dot. One is here and one is here. These are capacitively coupled to this gate voltage and tunnel coupled to the source and drain side. And we can, and for this double quantum dot, we have seen a honeycomb shaped uh, charge stability diagram. So that means, so if you look at this region, this constant charge region, this is the region where current is zero. But if you look at this triple point, let me erase it. So if you look at this triple point, for this triple point, there is a triple degeneracy, and we can see the flow of current. Current is non-zero whenever we are in the triple point region. So what does this mean? And you can see that. So this means if you change this gate voltage uh, in a more controlled manner, so that you can see this 0 0 state and 1 0 state, or 0 1 state, or 1 1 state. So you can get all this state by controlling this U1 and U2 voltage. So that means you will see the unidirectional flow of electron. There won't be any backward tunneling, and uh, there won't be any backward tunneling, but it's still possible to see the co-tunneling here. So for that, so this is one of the, I think, current versus voltage graph for a metallic single electron pump. So if you apply a frequency of 4 megahertz, you can use the relation I is EF, and you can calculate that the current would be in the order of I think 0.4 picoamp. And from that, you can see you are getting a graph like this. And if you change the voltage, then the current direction, it changes. And the relation between frequency and current is linear. I is EF. So now let us see the issues with this metallic electron pump. So one of the issue is that there won't be any backward tunneling, and it's still possible to reduce the co-tunneling, and by increasing the number of island, I also will see a improvement in accuracy of the measurement. Okay, so I think I can skip this part. I think it, it's well explained in the lecture. Or if you want me to cover it, let me know. So I'm just skipping this part. Okay. For the second part, we have semiconductor single electron pump. So if you look at this, for the issues with this metallic single pump was the current level. If you recall, they are in the order of picoamp. There is low current level, and we can't uh, regulate the tunnel junction resistance because they are metallic. So it's not possible to control in a flexible manner what is the tunnel resistance of this uh, the current standard. But if you use a semiconductor single electron pump, because the tunnel junction they are made of semiconductors, so you can control the tunnel resistance of this single semiconductor single electron pump. So this is, and also one of the issue with the metallic one is that they mostly operate in the megahertz range, so in the low frequency range. So to operate in a high frequency range, we need the semiconductor single electron pump. Okay. So if you see this graph, the first graph, from the these are semiconductor single electron pump, and you can see that you can control this tunnel barrier in a flexible manner, and you can make the electron tunnel one by one in a more flexible manner. Okay. And the current that you will get, you can see that it is 150 pico. So current is much higher than what we can get in the metallic single electron pump. So is it okay if I skip all this part, or let me explain it in a brief? So if you look at the second plot, they are for a silicon room temperature single electron pump. Okay, so this is the schematic, and from this graph, you can see that you are regulating the voltage of one of the gate voltage, and you are making the electron tunnel to this. Then now, in the next case, we are now increasing. You are making this gate voltage such that the electron is it is locked in that uh, region, and now you are varying the voltage of the second one, and you make the electron tunnel to the drain side. Okay. So it's just that you are controlling this two gate voltage so that you can see more controlled transfer of electron from the source side to the drain side. Okay. And then this is all. So now what we have, so we know the current standard, we know the voltage standard, and we know the resistance standard. So we know three standard. One is voltage, resistance, and the current standard. For the voltage standard, we use the quantum Hall effect. Sorry, this is for inverse AC Josephson effect. And for resistance standard, we use quantum Hall effect. And for this, we see the Coulomb blockade oscillation of single electron charge. And for the voltage here, UJ, you can write it as NF by KF. And the resistance here, you can write it as RK over I. And the current of the current standard, you can write it as QS FSET. Okay. So now let us combine all these together. quantum version of Ohm's law. Give me a minute. So let me know if you have any doubt till now. Okay. So if you combine all these voltage, current, and resistance standard, then we'll see the quantum version of Ohm's law, where we can express Uj is V is IR, so I is CT, RH. So now let us see what is the accuracy of this relation, how accurate this relation is. So for this, one experiment has been done. So this is what we call the quantum triangle experiment to measure the accuracy of current standard and voltage standard and the resistance. So I saw you writing something in the chat box. So let me know if you have a doubt. Okay. So if you express this quantum version of a Ohm's law, and if you put all this relation that we have seen earlier, all this relation to this Ohm's law, what you will get is Kj Rk Qs, it is In Fs over Sat, which should be equal to 2. So that means if you want to calculate the accuracy of this Ohm's law, so you need to check how this measurement is deviating from this exact value of 2. So this is what has been done. So for that, what you can do is that so you can just take that there is an error in calculating QS and there is an error in calculating the Hall resistance and there is an error in calculating the Kj constant using the voltage standard. So that means you can write QSS. Ideally it should be E, but there is an error of epsilon E. And let us say Rk is H by E square 1 plus epsilon K and Kj is 2E by H ideally, but there is an error to it. So we are just using this error to see how accurate will be the measurement. So that means if you take the product of this AJ US and RK. So this will give, this should be equal to 2, 1 plus epsilon J, epsilon K plus epsilon E. This is this product we have expressed in terms of this. So we just take the first order. So we haven't take any cross term like epsilon J, epsilon K or epsilon E, epsilon K. So we just check what is the first order, error in the first order. Okay. So ideally it should be equal to 2. But if these values are much less, then in that case, we can say that the measurement are accurate. So like in the resistance standard, we see that delta RK, it is on the order of nano. And in the voltage standard, this is, we have seen a value 10 to the minus 21. So in similar case, if this errors in the current, this Ohm's law, if it is much less than the threshold of the current measurement, then we can say that this relation is accurate. Okay. I think this is what has been checked. So if you look at this delta E over E, the errors are quite less. So I think, where is this error? Yes, this is. So delta E by E, you can see that they are in the order of 10 to the minus 4. So that means we can say that these relations are accurate for our measurement. Okay, I think this is all about the concept of week 11. Now let us see and let us solve few problems related to this concept. Okay. So first we'll see few problems related to week 10, then we'll solve week 11. Okay. So I hope the screen is visible. If not, let me know. For the first question, we have a RF single electron transistor which is connected to a LC tank with resistance L is 220 nanohenry. So let me write down the values. Given L is 220 nanohenry and total capacitance C is given 0.4 picofarad. Assuming that the SCT resistance is large enough not to shift the resonance significantly, what is the approximate resonance frequency of this tank circuit? So you need to calculate the resonance frequency of the tank circuit. So I will give you some time to calculate it. Let me see whether you are able to solve it or not. If not, I will go through in details the steps. Okay. So to calculate the resonance frequency of this ideal LC tank circuit, so whenever you have a LC circuit, you can write the resonance frequency of this LC circuit as 1 by root over of LC. Sorry, 1 by 2 pi root over of LC, or omega is 1 by root over of LC. So both L and C are given to us. So that means F0 is 1 by 2, 3.14. L is 220. I think nano Henry. 10 to the minus 9. Capacitance is 0.4 picofarad 10 to the minus 12. So just check whether the answers are correct or not. This will give, I think, 8.8 into 10 to the minus 20. And overall, it will give a frequency around 536 megahertz. And if you look at the options, option D is quite close to the answer we are getting. So answer would be option D. So just remember to, if you want to find out what is the resonance frequency of a LC tank circuit, the frequency relation is, or you can just write, remember omega is 1 by root over of LC, or F is 1 by 2 pi root over of LC. So is this clear? Okay, so for the next part, it's given for a RF SET readout circuit. You want a operating frequency around 800 megahertz using an inductor L150 nanohenry. Assuming resonance is dominated by the LC values, what is the total capacitance C, which is required to get this operating frequency around 800 megahertz? So can you please solve it and let me know the answer? Okay, so okay, let me solve it so that you can check the answer. Okay, I think you remember the formula, which is the formula in our previous questions. So it's given F0 is 800 megahertz and L is given 150 nanohenry. We want to know the capacitance. So the relation is same. F0 is 1 by 2 pi root over of LC. So 2 pi F0. So you want to calculate C. So that means this is 2 pi F0 square times L. F0 it is given 800 megahertz. So pi. So the units are important. You just check whether you are using the correct order also. Okay. And L is 150 nanohenry. I think this will give a value around 0.26 picofarad. Okay. Cross check once whether you are getting it or not. Option C is the answer. Do you have any doubt? Okay, so let us go to our next question. The question says a radio frequency single electron transistor was configured using a 400 nanohenry inductor. The resistance value of SCT is found to be 16 kilo ohm to achieve a perfect 50 ohm impedance matching of this coaxial line. What is the capacitance of the high frequency tank circuit at this point? Would you able to solve it? So there is a impedance matching of SCT with the tank circuit as well as the coaxial line. Uh, if you recall the SCT impedance, it is decided by the resistance of SCT, resistance of uh, SCT and the inductance and the capacitance of the tank circuit. So resistance of SCT is acting like a variable resistance. So if you vary the resistance, then you will get a value of resistance where the impedance of this tank circuit will match it with the coaxial line. And whenever this match, there won't be any reflection. So you will see a complete transmission there. No, it's not based on same formula. So if you recall in the previous formula, F0 is 1 by 2 pi root over of LC. So this is just to calculate what is the resonance frequency of the tank circuit given if you have a inductance and capacitance. And if you recall, in the radio frequency SCT, we attach this SCT to a external tank circuit, LC circuit, and we can represent this SCT by some variable resistance RD. So this combined circuit, the LC circuit and the variable resistance of this SCT, they will have a resonance. Sorry, they will have a impedance. And now we are sending a signal to this coaxial line, which has a impedance Z0. So you have a impedance Z of SCT combined with the tank circuit. Also the coaxial line where you are sending the RF frequency, it also has some impedance. So, and whenever this doesn't match, so there will be reflection. But if Z equal to Z0, there won't be any reflection. So in the question, it is saying that this tank circuit, it is perfectly impedance match to this coaxial line. And the impedance is also given, it is 50 ohm. So that means you are given Z, which is equal to Z0, and it is 50 ohm. Okay. It is given. Next thing we are given is that this impedance matching, this we get around the variable resistance of SCT, which is 60 kilo ohm. So that means what we are given now, RD is 50 kilo ohm. Sorry, 16 kilo ohm. Kilo ohm or ohm? Yes, kilo ohm. And another thing is given is that for this tank circuit, we have a resistance inductance value of 400 nanohenry. L is 400 nanohenry. So we want to calculate the capacitance for this perfect impedance matching condition between the tank circuit as well as in the coaxial. So for that, if you recall at the resonance, so this tank circuit, it has a complicated impedance relation. So you must have seen, I think the slides is there. Yes, this is the okay. So this is only the problem set. Okay. So this tank circuit has a complicated impedance relation, but at the resonance, you can write this Z as L by CRT. Okay. At the resonance, we have, or by resonance, we mean there is a impedance matching with the coaxial line or the wire where we are sending the RF signal. So this Z is equal to Z0, which is 50 ohm, and we want to calculate the capacitance. So that means L by CRT. This is equal to 50 ohm. L is given, RD is also given. We can easily calculate C now. So that means C is L by 50 ohm RT. L is, I think, 400 nanohenry and RT is 16 kilo. This is 400 to 10 to the minus 9. RT is 16 to 10 to the 3. So you will get around 0.5, I think. Yes, 0.5 picofarad. Okay, answer would be option A. So is this clear? Whenever there is a impedance matching, you can use this relation and you can equate it to the impedance matching, impedance of this coaxial line to get the value of L or C or R. So is this, do we have any doubt in this problem? Otherwise, we'll move to the next one. Okay, so if there is no doubt, let us move to our next question. In the next question, we are given a radio frequency SCT is set up to realize a perfect 50 ohm impedance matching with the external circuit. What is the reflectivity? What is the reflectivity of the signal at the resonance? I think this should be reflectivity. Can you guess what will be the answer for this? You have a radio frequency SCT and you have a perfect impedance matching with the external circuit. What is the reflectivity of the signal at resonance? Option A. Yes, this is correct. So if you recall, I think you must have used this one. Reflectivity, it is given by Z minus Z0 over Z plus Z0. Z0 here is the impedance of coaxial line and Z is the impedance of tank circuit. And if there is a impedance matching, Z is equal to Z0. So that means gamma is, or the reflectivity is 0. Other than this impedance matching condition, if we have any other values of C or R or any value of L so that the Z is different, then from that case, the reflectivity will increase. So what I was saying is that gamma, it is given by Z minus Z0 over Z plus Z0. And you have a tan circuit here and you have a coaxial line here. This is Z, this is Z0. And typically at the resonance, we have Z equal to Z0. So that means there will be perfect impedance matching and Z, because Z is equal to Z0, the reflectivity gamma would be 0. Now let us say in the tank circuit you have you change the impedance by changing. You can recall Z is given by L by CRD at the resonance. Now you are changing either L, or let's say you are changing C, or you can change RD. So that this perfect impedance matching condition is now changed. So for this case, what will happen? Because now Z is not equal to Z0. So you are taking different value of L, C, and R. So for that case, the reflectivity will now increase. So no matter you decrease the resistance or decrease the inductance or increase it, no matter what you do, if you change it from this ideal value, the reflectivity will increase. Yes, gamma, it is the reflectivity. Okay, so I think this was all about the questions of week 10. Now let us see the problems related to week 11. Okay, question number 1, I think you will be able to guess the answer. Question 1 is the universal practical standard for electrical resistance is based on quantum value Hall effect or quantum spin Hall effect or quantum Hall effect or all of this. What do you think the concept that has been used as a practical standard for electrical resistance measurement? Option A, quantum value Hall effect. Option B, quantum spin Hall effect. Or option C, quantum Hall effect. Or option D, all of these. The questions may seem confusing, but the answer to is quantum Hall effect, not all of this. Because quantum value Hall effect, this is a different concept, which is quite different from quantum Hall effect. Although we say quantum value Hall effect, but it is different from the actual quantum Hall effect. Okay. Similarly, quantum spin Hall effect it is also different. So for resistance measurement, what we need is that quantum Hall effect. Okay. So answer would be option C. Don't get confused between this valley and spin. Although they say this is Hall effect, but the mechanism are quite different. So that is why the answer would be option C. Question number 2. In the integer quantum Hall effect, the Hall resistance RH is defined H. RH is E square by H, or option B, RH is I times E square by H, or option C, RH is H by I square, I is integer, or option D, RH is H by E square. In the integer quantum Hall effect, what is the value of RH? So if you recall, RH is RK by I, right? And RK is H by A square. I. So RH is H by A square I. So that means option C is the correct answer to it. Okay, not A square by H. So is this clear? So these are all based on direct formula. So you just need to remember the formula. Okay. Question number 3, it's a conceptual question. It says one of the biggest advantages of using quantum Hall effect as a resistance standard is that the quantized resistance. Option A, the quantized resistance depends on the material of the sample and its carrier concentration. Option B, it depends on the geometry, width and length of the Hall bar. Option C, it is independent of material, geometry and impurities. Or option D, quantized resistance changes with temperature even at cryogenic conditions. So what is the biggest advantage of using quantum Hall effect as a resistance standard? Whether the quantized resistance depends on the material of the sample and its carrier concentration, or it depends on the geometry of this Hall bar, or it is independent of material geometry and impurities, or it changes with temperature even at cryogenic condition. Okay, so the correct option to this question is option C. If you recall, I have the slides also. If you recall this, the second slide, why do you can see that from all these three plots, you can easily see that this resistance, the error in the calculation of resistance, which is delta RH, it is in the order of nano. So that means even if we are increasing the width, or if we are increasing the geometry or the temperature or the carrier concentration, the errors are quite less. So that means error is less means the resistance is not quite fluctuating even if we increase, even if we change the geometrical parameter or if you take different material. So that is why we use this uh, uh, quantum Hall effect as a resistance standard. Okay, so it is independent of material, geometry, and impurities. If it does depend on geometry, so that means depending on the geometry, the resistance will change. So that means we can't use it as a resistance standard. To use it as a resistance standard, that means even if we change some external parameter, it can the standard that we are comparing. So we have an uh, uh, unknown material that we want to measure the resistance, and we have a standard. So we are measuring the resistance of this material using this standard. But if we now increase, and if you recall that resistance, it is not a material properties. So that means uh, it all depends on what is the voltage we are applying, what is the current flowing through it. And if we increase the dimension, if the standard is showing the different behavior, so that means we can't use it as a standard. So to use it as a standard, the value should be remain unchanged and doesn't it shouldn't depend on any external parameter. So that is why we use this quantum Hall effect as a resistance standard. So I hope it's clear. If not, let me know. Yeah, I will try to explain it further. Question number 4. Which of the following statement is not true about the quantum Hall resistance standard? Option A, it provides reproducibility better than 1 part in 10 to the 9. Option B, it is used by National Meteorology Institute worldwide. Option C, it requires no cryogenic temperature or magnetic field. Or option D, it is based on a fundamental physical constant. What is not true for the quantum Hall resistance standard? So that means what is not true for a quantum Hall experiment? Okay. So the correct option for this question is option C. This quantum Hall resistance, they are because they are standard, they are already used by the NMI worldwide. Okay. But if you recall the quantum Hall experiment, we require magnetic field to see these plateaus. And if you consider the gallium arsenide one, we still need cryogenic temperature. For graphene, it is not required. We can see the quantum Hall effect even at high temperature, which is around 100 Kelvin. But if you consider the gallium arsenide one, you still need the cryogenic temperature. And magnetic field, we always need magnetic field to see the quantum Hall effect. If there is no magnetic field, we won't see any quantum Hall effect. We won't see this plateaus in the resistance. Okay, so that means option C is not true for the quantum Hall resistance standard. Question number 5. The quantized Hall resistance on the ith plateau is given by RH is H by I square. What is the main metrological significance of this integer I? Option A, it represents the measurement error of the resistance standard. Option B, it levels different materials used as quantum Hall devices. Option C, it is an adjustable fitting parameter used to correct for temperature effect. Or option D, it sets different discrete resistance value that can be chosen as a standard multiples or fraction of the ohm. So what does this question ask is you are given RH is H by I square. So what is the metrological significance of this integer I? Okay, the correct option is option D. So it's not a adjustable fitting parameter, which is correct for temperature effect. Okay, so it's like it's an integer, and if you vary the integer, so you will get different value of RH. So H by you can get H by 2 square, you can get H by 3 square, or you can get H by 4 square. So that means you can, and this I means different plateau region. So you can flexibly choose whichever plateau region you want, and you can use it as a some standard multiples or fraction of ohm so that you can measure the resistance of some unknown device. Okay, so this is just um, I is just it sets the discrete resistance value so that This can be used by standard laboratory to select any particular plateau so that they can measure the resistance of some unknown metal. Okay. Okay, so let us see question number 6. In the context of voltage standard, what is the primary role of inverse SE-Josephson effect? Option A, to suppress the thermal noise in superconducting circuit. Option B, to convert a DC voltage into a quantized AC current. Option C, to generate a precisely quantized DC voltage from a applied microwave radiation. And option D, none of the above. So it basically asks about what is this inverse AC-Josephson effect is doing in a voltage standard. Whether it is suppressing the thermal noise in the superconducting circuit, or it converts the DC voltage to a quantized AC current, or it generates a precisely quantized DC voltage from an applied microwave radiation, or none of these options are correct. Uh, Option A, it is not the correct option. So the correct is option C. So if you recall, when there is no AC voltage applied, or there is no inverse AC Josephson effect, you will see a graph like this, right? But once you apply a AC voltage as well as the DC voltage, you will see a step like which we call this as a Shapiro steps. So when we apply microwave radiation, that we say we are applying AC voltage, we'll see a precisely quantized DC voltage. Okay. Option C. Question number 7. Which expression correctly gives the quantized voltage step produced by the Josephson junction in the inverse SA Josephson effect when irradiated at frequency F? So what is the expression for the voltage, quantized voltage you are getting in the voltage standard using the inverse just SA Josephson effect? Is Vn. Okay, so just remember the formula. Vn is N. Vn for a voltage standard, it is directly proportional to F, and there is a constant N and K. And Kf is 2E by H, so N is H by 2E times F. So option B, I think. So option B is the correct option. Question number 8. Why are arrays of many Josephson junction used in practical inverse AC Josephson voltage standard rather than a single junction? So why we are using more Josephson junction instead of one? Option A, arrays eliminate the need of cryogenic temperature. Option B, a single junction cannot exhibit quantized voltage step. Option C, arrays ensure that the frequency of the applied microwave is increased. Or option D, arrays allow the total quantized value to reach practical level of calibration. So in the voltage standard, where we use the inverse AC-Josephson effect and we use the Shapiro steps, why we are using arrays of junction instead of one? So what is the main reason behind that? And as we have seen, this Vn over a single junction, you can write it as N H by 2E times F. F is the frequency, H by 2E, these are constant, and N is the different Shapiro steps. The answer is in this formula only. Okay, so just see what will happen when we change the frequency and what is the value of voltage you are getting from a single junction, whether this value can be measured by the practical level. Okay, so let me just go through this solution. So if you look at the single junction, this is the this is showing just the Shapiro steps, and F is the frequency. So that means if you just apply, let's say, frequency 1 gigahertz, then the VF or VN you can, when N is 1, you can get it around 2 microvolt. It's around that value. So that means for this amount of frequency, you are still getting a voltage in the order of microvolt. And this voltage, it's not quite a practical value to measure the voltage. So for to get a practical value, it should be in the order of volt or in 10 volt or more than that. But here we are saying that even if we apply 1 gigahertz, we are getting a voltage in the order of microvolt. And if you want to increase the voltage, that means we need to increase this frequency. And for a superconducting junction, which is the Josephson junction, there is complexity if you increase the frequency more than some value. So to avoid that, what we do, we make an array of Josephson junction. So let's say we have 10 arrays of Josephson junction. So for that case, the Vn, the V total, you can write it as the number of Josephson junction times the what is the voltage of a single junction. And using this, you can increase and get a practical value of voltage that you can measure. And if you recall, in the lecture, we have seen that if N is in the order of 20,000, then you will get a Vn of V total of 10 volt, which can be measurable. So that is why we are using a array. So answer would be option D. Arrays allow the total quantized value to reach the practical level of calibration. Okay. Question number 9. So, why is the longitudinal resistance, which is Rxs, required to be very small when while using the quantum Hall resistance as a resistance standard? Option A, Rxs directly control the quantized resistance H by I squared. Option B, Rxs controls the contact resistance and is unrelated. Or option C, a small RXS indicates system is well within the quantized plateaus, ensuring accurate RXY. So why would the RXS should be low? So for this answer is option C. Okay. So if you recall, or I think I have the picture also here. So from this plot, you can see that whenever this Rxx is low, we are getting a well-defined plateaus. So in the plateau region, Rxs is low. So that is why the Rxs should be low to get a well-defined plateau. So answer would be option C. Question number 10. What is the key advantage of using graphene-based quantum Hall devices for resistance standard compared to the traditional gallium arsenide or aluminum gallium arsenide devices? Option A: graphene devices completely eliminate the need for cryogenic cooling. Option B: graphene devices allow continuous tuning of H by square by changing the carrier density. Option C, graphene devices produce non-negligible multiples of H by E square, giving more resistance value. And option D, graphene devices can exhibit robust quantization at high temperature and lower magnetic field. So what is the main key advantage of using graphene as a resistance standard as compared to the traditional gallium arsenide or aluminum gallium arsenide based devices? Can you guess the answer? Okay, so the answer for this is option D. So we haven't covered the non-integer multiples of h by square, which is anomalous quantum Hall effect. But the main reason we are using graphene is that, if we recall this slide, yes, this one. So you can see that even if you are increasing the temperature to 100 Kelvin, the graphene can show the wider plateaus. Okay, so that is why we use graphene, so that because they are quite robust, the plateaus are well extended for a wide range of magnetic field. So that is why graphene devices, it can exhibit robust quantization at high temperature and low magnetic field. So this is the main reason why you are using the graphene as a resistance standard instead of the bulk one, which is gallium arsenide or aluminum gallium arsenide. Question number 11. The inverse in inverse AC Josephson effect refers to the conversion of DC voltage into microwave frequency or microwave frequency into quantized DC voltage steps, or option C, DC current into AC voltage, or option D, AC current into DC resistance. Uh, if you recall, in the inverse AC Josephson effect, V is V0 plus nu cos omega t. So that means we are applying a AC voltage, and this leads to steps in the current, Shapiro steps. So that means in inverse AC Josephson effect, the microwave frequency, it is turning to quantized DC voltage. So this is what we mean by inverts in the inverse AC Josephson effect. Option B. Okay. Which physical system can be used to realize the quantum Hall resistance standard? Option A, bulk three-dimensional metal. Option B, insulating ceramic with high resistivity. Option C, two-dimensional electron gas in semiconductor heterostructure. Or option D, superconducting wire at room temperature. Yes, the answer is correct. The correct option is option C. So you can use 2D electron gas in a semiconductor heterostructure to see the quantum Hall resistance. Question number 13. Which physical effect is fundamentally used in quantum current standard to precisely control the tunneling of individual electron one at a time? Option A, Josephson effect. Option B, quantum Hall effect. Option C, Coulomb blockade effect. Or option D, Aharonov-Bohm effect. Which of this concept is used in the current standard to measure the tunneling of single electron one by one? So correct option is option C. So Josephson effect, particularly with the inverse AC Josephson effect, this is for voltage standard. Quantum Hall effect, it is for resistance standard. And Coulomb blockade effect, it is for the current standard where we trace the electron one by one. Okay. Question number 14. In a single electron pump used as a current standard, a single electron is transferred per cycle at frequency F. The resulting quantized current I is given by I is E by F, or I is E times F, or I is H E by F, or I is 2 E times F. You are given a frequency and there is a tunneling of single electron per cycle. Yes, option B is the correct option. So I is E by time and 1 by time is nothing but frequency. Okay, question number 15, it's a numerical one. A Josephson junction is irradiated with microwave frequency of 70 GHz. For the inverse AC Josephson effect at the first Shapiro step, that is n equal to 1, What is the quantized DC voltage generated across the junction? So you are irradiating this Josephson junction with frequency 70 gigahertz. And it's given you are in the n equal to 1 superior step. So what is the quantized value of DC voltage that you can get at this superior steps? Just recall the expression for quantized voltage that you will get in the voltage standard. Just use that, then from that you can calculate what is the quantized DC voltage. Okay, so let me go through these steps. So if you recall in inverse Josephson effect that we use as a voltage standard, the expression is Vn is N F by Kf. Kf here is 2E by H. And this already has a value of 483.6 megahertz per microvolt. That means this is 483.6 into 10 to the 12 hertz per volt. And n is given, it is superior step is 1. So, and frequency is also given. So that means the quantized DC voltage that you will get at n equal to 1, it is F by K. F is 70 gigahertz, 19, and Kf is 483.6 into 10 to the 12. This is volt. And this will come around 0.145 millivolt. Option D. So is this clear? Just recall this relation, then you can easily calculate the value. If n is different, then you can take n equal to 2, 3, but here it is given n is 1. Okay. There is a semiconductor single electron pump, which is a gated quantum dot, and this achieve a gigahertz range operation. If it pumps at 1 gigahertz, what is the resulting current? So you are given the frequency. What is the current that you can get in a semiconductor single electron pump? Can you guess the answer? Okay, so let me just go through these steps. So you are given the frequency and it is a semiconductor single electron pump. So you can write use this relation I is E times F is 1.6 into 10 to the minus 19 and frequency it is given 10 to the 9. So this will be 160 pico. So answer would be option B. Is it clear? Is this question is okay? So for question number 17, this would be our, I think, last question to solve today. Uh, it says which of this following is correct for the use of a many junction turnstile over a single junction metallic turnstile. Option A, reduced backward tunneling. Option B, suppressed co-tunneling. Or option C, improved accuracy. Or option D, all of the. So why do we use many junction turnstile over a single junction turnstile, metallic turnstile? Yes, the correct option is option D, all of the. I think, should I do it or skip it? Okay, so let's see the other question in our next lab session. So let me just know whether you have any doubt. Yes, you can ask for that. Do you want me to unmute you? Let me. Okay, the exam preparation is quite, it's not that difficult. So, one thing I would suggest is that the concept. You need to go through the concept again and again in a repetitive manner so that you can see that there are a lot of information and and there are a lot of conceptual question also. So the concept should be clear in your mind so that and the concept would be clear if you go through the concept in a repetitive manner. So I would suggest you to go through the concept and slides and also the whatever that has been taught in the class. And uh, live class and assignment. Yes, these are quite enough. You don't have to solve any more questions. Okay. The question, most of the time, you will see that the question will be in a part you have skipped in the live section or in the during the recording. You can see that all of these assignment question other than the numerical one. So for numerical one, you need the formula, you need some of the concept so that you can use that formula. You just need that thing. But for conceptual wise, you need more than that. So whatever in the assignment, the question that has been asked in the assignment, it's all in this live session as well as in the recording in the classes that has been taught by professor. So that means you don't need to do any more question other than this live session and assignment. But if you have time, then you can do that. But I would suggest first go through the concept as well as the formula again and again. Go through the lectures or the live session. Go through that, then it will be enough for. And one thing I need to add is I have uploaded the PDF file of this assignment in the Google Drive link. So I have, I think, uploaded up to week 5, or I don't recall now. But just go through the if you don't want to revisit the uh, video link again and again, you can just, if you want to just solve the problems that I have discussed in the live session, then you can directly go through the Google Drive link. So there are files in there, so you can just go through, look after the files, and just check whether uh, you are comfortable in that. So Google Drive link, it's already there in the Google, in the sheet that has been shared with you. Okay, in the course website, there should be a, I think there is a link to get the recording link for this live session, and in that Google Sheet there is also link for the Drive link. Okay, if you click on that Drive link, you can get a folder where I have uploaded the files. Uh, there is no time, so I want follow live session assignment. Yes, it's enough live session and assignment. It's quite enough to pass the exam and to. I think all these are. You don't need to do extra. Just go through the concept and the assignment and understand it conceptually. Okay, don't just recall the answer. Understand it also. That will be enough. Uh, where I can see. Okay, Google Drive link is there in this sheet. I think that is fine. Uh, uh, one, if you have any doubt and ask during preparation. So it's not possible for me to say the mail ID, but one thing I can do is that whatever doubt you have, you can ask me in the last live session. And also, I think, yes, that is all that I can do from my side. Okay. So, thank you for joining the session. We'll meet next Friday, same time from 6 to 8, to to see the concept of our last live session. So go through the concept and just let me know if you have a doubt in our last live session. So for now, goodbye everyone.